All right, in this video, I want to do an example of a problem similar to this homework problem. The idea is that if you watch me do a similar problem, that will hopefully help you solve this particular problem. So the problem I'm going to work is something that looks more like this. Instead of having plus, minus, plus, I'm going to have minus, plus, minus, and my numbers are going to be a little bit different than the numbers that were in here. But hopefully you'll be able to get the hang of how to do the problem. So the first thing I need to do, if you'll notice that all of these are in nanocoulombs and all of my distances are in centimeters. So the first thing I need to do before I do anything else is I need to convert the nanocoulombs to coulombs, and I need to convert my distances to meters. And again, the reason for this is in electricity and magnetism, the units assume that you're working in newtons and meters and coulombs, not in centimeters and not in nanocoulombs. So we really have to do the conversions in this case. So if I go through here, remember nano is 10 to the minus 9, so this would be minus 4.53 times 10 to the minus 9 coulombs. This would be 2.90 times 10 to the minus 9 coulombs. This is minus 2.93 times 10 to the minus 9 coulombs. Okay, and then for the distances, again, there are a couple of ways you can convert the distances. What I'm going to do is centi means I want to move the decimal to make a smaller number, and centi is I want to move it over two places. So this would be 0.0104 meters. Another way you can do this is, remember, centi is 10 to the minus 2, so you could write this as 1.04 times 10 to the minus 2 meters, and either would be correct for this. So this would be 0.0115 meters, or 1.15 times 10 to the minus 2 meters. And then my third distance would be, try to do it this way. There we go. 0.0151 meters, or 1.51 times 10 to the minus 2 meters, or 0.0130 meters, or 1.30 times 10 to the minus 2 meters. Okay, so now that I have the unit conversions in, so the idea is that I ask you to calculate each of the electric fields from each of the charges individually at this point, and then add them together to get the total field at this point. And the idea is you would just, the field, the total field is going to be the field from each one, or the sum of the fields from each one. So this way, if you get one of these wrong, you'll know it, and that way you'll know which one specifically you need to concentrate on. And then the B part, it's similar, only you're looking at this point here rather than this point here. And again, you calculate the field from each of the charges at this point, and then add them together to get the total field at that point. So that's what we're going to be doing. So first thing I want to do is I want to find the electric field from this Q1. So remember, the electric field from a point charge Q is KQ over the distance squared. And then because electric field is a vector, I need to include the vector information. For this problem, you were specifically told to say that to the right is the positive direction. So that means that this way is the positive direction. I'm going to say it's the x direction. Okay. So the r hat here, remember, is the vector that points, it's a unit vector, it's that points away from the charge toward the field point. And it doesn't care about what the sign of the charge is. It always points away from the charge. Okay. So for Q1, okay, the vector that points away from this charge at this point would be this direction. So this would be R1 hat, and that's going to be plus X hat. So that's what I'm going to use for that. Okay, so the electric field from Q1 is going to be K times the charge divided by the distance from the charge to the field point. That distance here is going to be D1. That's going to be squared. And as I said, the R1 hat here is plus X hat. Okay, so if I put this all together, so I have my K is 8.99 times 10 to the 9 newtons meter squared per coulomb squared. My charge is 4.53 times 10 to the minus 9 newtons, or coulombs. Remember, I've got my plus X hat here. And all of this is going to be divided by my D1. They're squared. Okay. So I want to put this in my calculator. Okay. So I'll bring this up here. So hopefully you can see what I'm doing in my calculator for this. Okay. So I'm going to do 8.99. I know a lot of students like to use the times 10 to the 9 notation because it looks exactly like that. I would encourage you to, instead of having to write all of this out, a more shorthand way that calculators understand this is to use this E key. So I want to do 8.99 times 10 to the 9. That would be exponent E. That's the same thing as times 10 to the 9. Okay, and then times, then I have minus 4.53 E minus 9, and divided by 0.0104 squared, and that's going to give me my 3.765 blah 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 blah. I also want to point out while I'm thinking about this is that at least for the TI 36X Pro, you have the option of converting between two different modes how it displays the numbers. I've got it set up in scientific notation. You see I have that there. I could set this into kind of the normal mode like that. And then if I exit and I do the same problem, it writes it out all like that, which again, my preference is to do it, particularly when you're dealing with electricity and magnetism. It'd be nice to just have it in scientific notation. So I'm going to set my calculator specifically in that mode and then quit. Okay, and now I have it back in scientific notation. So I can write this as minus 3.765. Okay, I think I'm going to generally try to keep 2 decimal places. So I'm going to keep an extra decimal place at the end for when I calculate the final value, when I round it to just 2 decimal places. Well, let's go ahead and do another one, just to be on the safe side. So 10 to the 5. Okay, and then for the units, if I look at my units here, I have my coulomb here, cancels one of these. If I bring that square in, this meter cancels this meter squared. I'm left with newtons per coulomb, which is good. That is my unit for electric field. And then I have my plus X hat. So the actual direction for this would be, since it's negative, would be this way in the minus X hat direction. Okay, but that works out well for what we're doing. So this is the electric field from Q1. Okay. So now I want to do the electric field for Q2. So that's going to be K Q2 over R2 squared R2 hat. So the R2 hat, again, I want the vector that points away from this charge at this point. That's going to be this direction. So R2 hat is minus X hat in this case, because it's in the opposite direction to what I said was the positive direction. Okay, so I have that. So this is going to be K Q2 divided by the R2 is the distance from the charge to the field point. That's going to be this distance here, the D2. So this is going to be D2 squared. And again, my R2 hat was minus X hat. So I'm going to have that. Okay, I'll move this down like this, I think. Okay. So this is going to be my K. I think I'm going to do my units first this time. So I'm going to bring the square in. And then this meter square cancels that. Coulomb cancels one of those. And again, I get newtons per coulomb, which is what I need, okay, for this. So this tells me I want to do squared, and I get 1.97. Oop, and I forgot my minus sign here. So this should actually have a minus sign on it. Q2, electric field from Q2, the electric field from Q3, and K Q3 over R3 squared R3 hat. Okay, R3 is the distance from the charge to the field point. So that's going to be D2 plus D3 plus D4. So I need to add all those up here. So D2 plus D3 plus D4 squared. And then for the R hat, I want the vector that points away from this charge at this point. That would be this way. So this would be R3 hat. Kind of running out of room here. And this is also minus X hat. So if I go back down here, I'm going to have minus X hat. All right, so if we put on our numbers, oops, 8. Minus 4. So again, the units, these will all be meters squared. Cancel with that one. That cancels one of these. We get newtons per meter, or newtons per coulomb, excuse me. And this is in the minus X hat direction. So again, I need to multiply by the two signs together. So my E3, my electric field from 3, is plus 1.6797 times 10 to the 4 newtons per coulomb X hat. Okay. So I have each of my electric field values. So the total field is just going to be the sum of each of the individual ones. So my E total, or my electric field at A, is going to be E Q1 plus E Q2 plus E Q3. So this is going to be so now if I add those together, yeah. So that would be the total electric field at that point A.